This is section 3-4, the section on parallel and perpendicular lines. So the key to this section is going to be that you can use the relationships of two lines to a third line to decide whether the two lines are parallel or perpendicular to each other. So we're going to be sticking with our theme of using deductive reasoning, and we're going to use theorems to show that if two lines are parallel or perpendicular to each other, then we can decide if they are parallel or perpendicular to a third line. So let's start out with some theorems. Our first theorem is going to be theorem 3-8, which says if two lines are parallel to the same line, then they are parallel to each other. So let's take a look at this in terms of a diagram. So let's look at an example. So let's say that we have three lines here. Call them A and B and C. And let's say A is parallel to B and B is parallel to C. So A is parallel to B, and then we have B is parallel to C. So notice that I'm using my notation here to show that these guys are parallel by putting the same number of markers on them. So then by theorem 3-8, I know that A is parallel to C because A and C are both parallel to line B here, so then that means that they're parallel to each other, sort of using our transitive property here. Next up we have theorem 3-9, and this one's kind of similar. It says, in a plane, if two lines are perpendicular to the same line, then they are parallel to each other. So again, looking at this in a diagram, let's say that we have our lines here. Oop. We have L and M, and then we have N. And they're both perpendicular to L, so L is perpendicular to N, and M is perpendicular to N. So then, by theorem 3-9, I know that L is parallel to M because L is perpendicular to N and M is perpendicular to M, so then L has to be parallel to M. Alright, now we have theorem 3-10, also kind of similar. So it says, in a plane, if a line is perpendicular to one of two parallel lines, then it is perpendicular to the other. So this one's pretty similar to what we just talked about. In this case, we're starting out with, again, lines L and M. Then we have line N here, and let's say N is perpendicular to L, and we know L is parallel to M. So let's go ahead and mark our diagram accordingly. N is perpendicular to L, and then L is perpendicular, or is parallel to M. So then I know by theorem 3-10 that N is perpendicular to M. So again, this says if a line is perpendicular to one of two parallel lines, then it's going to be perpendicular to the other one. So something to notice in our definition, or in our theorem 3-10, it uses the words in a plane. The reason that's important is because if they're not in a plane, then this theorem actually doesn't apply. So let's take a look at an example of a cube here. Okay, so let's say we're talking about segment AB and segment CD here. So these guys are parallel. And then let's also talk about segment AE here. Then AB, notice, is perpendicular to AE, and AB is parallel to CD, but because they're not on the same line, AE is actually not perpendicular to CD. AE is skew to CD, so this is why they need to lie on the same plane. Let's take a look at some notation. So we remember the notation for parallel is that we just draw like a mini pair of parallel lines. So if I wanted to say that line A is parallel to line B, I would say A is parallel to B. Now, the symbol for perpendicular is pretty much the same idea. It's going to be mini perpendicular lines. So if I wanted to say that L is perpendicular to M, or L is perpendicular to M, it's kind of like a mini perpendicular symbol there.